Now, let us study the radial heat conduction through a cylindrical shell. Now, this type of heat conduction is very important in electrical cables, where the current flows inside the inner copper wires and produce heat. That heat must be dissipated through the insulation so that the cable can work properly and last longer. Similarly, when heat is conducted through a tube in which some hot metal or some hot substance suppose is flowing, then we must know how that heat must be transferred through the cylindrical walls. So, let us take a cylindrical tube. So, this is the cylindrical tube of outer radii. Suppose I assume at this outer radii to be B and the inner radii from the center line it should be B and from the inner radii to be A. Let us take A and B, and the letter R is reserved for the thermal resistances. So, let the inner surface, cylindrical surface, be maintained at theta 1 temperature and this be theta 2. So, what happens? The heat flows along this. So, from inner to the outer in radial direction the heat flows. So, in order to study how the heat flows, again let us consider a annular region. This is the annular region that I am going to shade it. So, this is the annular region. So, this annular region has a radial r and this radial width, suppose I say x, so it is dx. So, the heat flows along this radial direction, along the direction x. Let the temperature here be theta and here be theta plus d theta. So, we have a cylindrical conducting shell of inner radii A and outer radii B. The conductivity of the medium, the conductivity of the material medium is K. The inner wall is maintained at a constant high temperature theta 1 and the temperature of the outer wall, outer radii be theta 2. Now, in order to study the heat flow, we have to consider a cylindrical element. Consider a differential cylindrical shell of radius x and radial width dx. Let the length of the cylinder be unity. So, unit length, that means radial heat conduction per unit length I will be talking, heat current per unit length. So, using Fourier's law of steady state heat conduction. So, we use Fourier's law. So, according to Fourier's law, the rate of heat flow dq by dt, which I will write as I, is equal to minus Ka d theta by dx. This is our law. When this law I am applying to this, it gives us I is equal to minus Ka. In place of area, I have to use the curved surface area. The heat flows through the curved surface area, that is 2 pi r L. But L I have taken as unity, presently I am writing, but that I will leave because L will be 1. In next step I will write. So, presently let it be here to tell that what this area is. Area of cross section is 2 pi r L, d theta by dx is d theta upon dx. We will integrate to get the desired result. So, what we will be doing is I is here, dx by this x comes here, minus 2 pi k L, let L be present, d theta. And if I integrate, then when theta 1 is the temperature here, it is x is A, when theta 2 is temperature here, x is B. So, I. Now, integration of 1 by x is log x, that is ln x from A to B, minus 2 pi k L theta 2 minus theta 1. So, heat current I is ln, we will first substitute B, then it is A, the limits is over, then minus I am bringing it inside, theta 1 minus theta 2. So, I, this is ln B by A, 2 pi k L theta 1 minus theta 2. So, I is equal to 2 pi k L by ln B by A theta 1 minus theta 2. So, this is the heat current. Now, we can find this, the thermal resistance of a cylindrical resistor is given by RTH is equal to, so you see this term, this is ln B by A upon 2 pi k into L. So, this is the thermal resistance of a cylindrical heat conductor. Now, let us see what is the temperature profile, that is how temperature will vary with distance. In order to calculate temperature varying with distance, previously I used that point that this is a shell and then I took some series combinations. Then what I will do next, here I can directly use this relation directly to calculate temperature. Let us see how we can do. Now, previously in that spherical case I took some series type situation. Here I will directly use the same result to calculate the temperature difference. What I do, suppose here temperature is theta 1, here it is theta 2 and I assume that this is theta at some value of x. So, in this way I can calculate theta directly. So, I will get I is equal to ln this x by A will be minus 2 pi k L, this is theta minus, this is theta minus theta 1. So, we wish to calculate theta. So, I will use I, this is ln, if I bring this A by x, then one minus will come, that will get cancelled here. So, theta minus theta 1. So, I have theta is equal to theta 1 plus this theta 1 plus this term, that is I upon 2 pi k L ln A by x. So, you see theta becomes theta 1 plus I. You recall I is equal to the temperature difference theta 1 minus theta 2 by thermal resistance, which is ln B by A by 2 pi k, you can see it is 2 pi k L. So, again that thing we will put, I is equal to theta 1 minus theta 2 by ln B by A upon 2 pi k L, and this is 2 pi k L again ln A by x. So, this 2 pi k L will cancel. So, you see theta becomes theta 1 plus theta 1 minus theta 2 by ln B by A divided by ln A by x. This is how theta varies with, this is the temperature profile of this cylindrical thermal resistor or conductor. Now, we will calculate at what value of x, this temperature will be the average temperature of inner and outer radii. Now, let us see at what radial distance, the temperature is theta 1 plus theta 2 by 2. So, what we do? We have to calculate the value of x for which theta is equal to theta 1 plus theta 2 by 2. So, thus substitute it, theta 1 plus theta 2 by 2, this is theta 1 plus theta 1 minus theta 2 by ln B by A into ln A by x. So, you just see if I bring this minus, so it will be theta 1, here it will be theta 1 minus, so 2 theta 1, so here minus theta 1 plus theta 2 by 2 is equal to theta 1 minus theta 2 by ln B by A into ln A by x. So, here you see if I cancel it, there will be minus 1 by 2 is equal to 1 by ln B by A into ln A by x. So, again if I multiply this here, it will be minus half ln B by A is equal to ln A by x. So, we can bring this minus here, so it will be A by B. So, ln this half means root over and minus means it will become A by B is equal to ln A by x. If I compare these two sides, I will get ln A by root A by B is equal to A by x. So, you see this is root A, root B. So, x is equal to root A B. That means, x is the geometric mean of the inner and outer radii. So, when x is equal to root A B, then the temperature is the average temperature of the inner and outer radii.